Hello everybody, this is Dr. Christopher White, and in today's presentation we're going to be looking at sedimentary rocks. So obviously sedimentary rocks is a very large subject and it's of great importance to earth scientists, so clearly there's going to be a lot of information we're going to have to deal with. So because of this, sedimentary rocks are going to be split up into two separate lectures. There's this lecture, which is going to be a little bit on the shorter side, and it's going to be focusing mostly on sedimentary rocks, some of the textures that we'll see in those sedimentary rocks, and some of the physical characteristics of sedimentary rocks. The second lecture is going to be focused more on environments of deposition. So it's going to be looking at the textures that we see in sedimentary rocks and how we can use that information to work out the environment into which that sediment was deposited. Okay, so let's get going on part one. So as no one was around millions of years ago to observe the deposition of the sediments that went to form sedimentary rocks, we obviously have a bit of a problem. So we have to use the principle of uniformitarianism. We're very familiar with uniformitarianism by now, hopefully. So it simply says if it's happening now, it happened in the past in the same way and normally at the same rate. So we can look at modern sedimentary systems and apply what we see to rock samples. However, in order to make such comparisons, we need to have a very solid bank of evidence and observations to support our inferences. So we can't just say, oh yes, that sedimentary rock is clearly the result of some kind of process in a river. We actually have to be able to say, right, well, what are the features of that sedimentary rock that tell me it probably formed in a river environment? So igneous and metamorphic rocks, as we've already touched on in the past, provide substantial evidence on the composition of the Earth, the process of plate tectonics, volcanism, changes in pressure and temperature, etc. But the vast majority of the information they give us is for the subsurface. When it comes down to actually what's going on the surface, only really sedimentary rocks are helpful, because sedimentary rocks have two features going for them. Number one, they preserve the evidence of surface processes that are responsible for the deposition. So we can see how the movement of running water, how wind, waves, the movement of glaciers has affected the sediment. The other thing about sedimentary rocks, which is great, is that many of them contain fossils. And of course, fossils are very useful to us. They allow us to date the rock, correlate the rock, but they also have important environmental information as well. So, sedimentary rocks tell us what was happening at the surface, be it on the land or the seafloor. So, what sedimentary geologists do in the modern world is they look at areas where sediment is being deposited, and we term these depositional environments. And what we're going to do is we're going to produce a set of criteria defining each depositional environment. So we're going to look at a whole range of different features. We're going to look at what type of sediment it is. We're going to look at how big are the clasts, how well rounded the clasts, how well sorted the clasts. Is there a nice sharp contact between the layers of rock, or does there, are there gradational contacts between the beds? And then we're going to look for things like fossils. We're going to look for sedimentary structures like ripples or crossbeds, and all that information is going to be helpful to us to actually work out what environment that sediment was deposited in, and therefore what environment the sedimentary rock formed in. So that's our challenge. So when we look at a sedimentary rock, we're going to look at a whole range of properties, but the first ones that your average geologist will look for first of all is the colour. Colour most of the time is pretty useless really when it comes to working out where a rock came from, but occasionally it can be helpful. We're going to be looking at the composition. What are the minerals that make up our sample? We're going to be looking for textures. Are there any kind of textures or structures within the sample, within the outcrop, that's going to help us work out what type of environment the sediment was being deposited into? If we're lucky enough to have fossils, obviously they are very helpful to us. We'll also look at the thickness of the layer of sedimentary rock, because that's also going to help us work out, or at least coarsely gauge, the possible environments into which the sediment was being deposited. And we'll also look at the relationships between the different rock layers. Because sometimes when it really comes down to it, if you look at a layer of rock, it's actually impossible to work out what depositional environment it formed in. However, if you look at the package of sedimentary rocks, you actually can work out what type of environment it formed in. And something like a delta is a classic example of that. The individual layers of sediment that make up a delta are actually, on the whole, pretty unspectacular, and they could have formed in a whole range of different environments. However, when you look at the whole package of sedimentary rocks formed as part of that delta, well, then all of a sudden you can see that, right, this is a sequence of rocks that was formed due to a delta. So geologists will make initial interpretations about the rocks that they observe based on these features. So, a half-decent geologist can walk up to a sedimentary rock and they can probably come up with some very, coarse ideas about, what type of environment this rock formed in. So, in terms of colour is most of the time pretty useless. However, there are two times when colour can be helpful to a geologist. The first instance is if your rock has a red colour, and more accurately, a rusty red colour. So rusty red coloured rocks are most likely to have formed in arid conditions. So you're talking desert or semi-desert environments. I will be clear though, that's not accurate all the time. For instance, very, very, very deep marine mudstones that form right on the abyssal plain can sometimes also have a very distinct rusty red colour to them. So if you see a rusty red coloured rock, it doesn't instantly mean it formed in a desert or semi-desert environment. It just means there's a reasonable chance it did. We can also have sedimentary rocks that have a slightly greenish tint to them, and in that instance they are more likely to have formed in marine environments. However, once again, green tinted sedimentary rocks, yes, there is a good chance they would have formed in a marine environment, but there are other instances where you can form sedimentary rocks that have a slight green colour to them. So, these are good rules to give you a general idea about the type of environment your rock could have formed in, but they are not 100% certain. So a geologist, once they've analysed the rocks in the cliff face, they'll take samples and analyse the rocks down a microscope to determine textures, minerals and fossils if at all present. We can also take our samples and we can subject them to chemical analysis, and you can do that in a couple of ways. There's a type of analysis called a point analysis, and that's when you analyse a very, very small area. So you'll just analyse a crystal, an individual crystal, and you'll get the chemical composition for that particular area. Or you can do what's called a bulk analysis, and that's when you take the whole rock and you'll typically dissolve it down in acid, so it essentially becomes a solution, and then you'll run that solution for a piece of lab equipment and you'll get the complete chemistry for the sample. So so geologists will visually observe the rock, we'll look at it down a microscope and visually observe it in greater detail, and if we really need to, we can also take it into a chemical lab setting and we can actually analyse individual crystals or the whole rock itself to get a lot of information about which can help us work out the environment of deposition. So this is your standard thin section. It's a pretty unspectacular looking thing. So most thin sections, this bit of rock here is going to be about 2.5 to 3 centimeters in length. And as you can see, it's polished extremely thin. So the layer of rock we have on this glass slide here is so thin that light will pass through most silicate minerals. And so when we look at it down a microscope, we'll see something like this. So this is a sandstone. So all of these grey crystals here, all of these grey blacks, all these kind of grey, black, brown crystals, these medium grey crystals, these light grey crystals. This is all the mineral quartz. And this kind of golden yellow mineral in between the quartz crystals is the mineral calcite. So what we have here is we have a sandstone which is cemented together by calcite. So, just by making a thin section, looking down very, very quickly, we can work out what the main minerals are. And this is also quite helpful if you are in something like petroleum geology. So if you're looking for a reservoir rock, the type of rock that could contain oil or gas, well, this rock would be absolutely terrible because there's no porosity, there's no permeability. So your oil wouldn't be able to, build up in this layer of rock. However, because it is impermeable, because there is no porosity or permeability, it would actually make quite a good seal. So oil would get trapped behind this layer of rock. So, analysis using a microscope can be extremely helpful. Now, another thing that looking down a microscope can do is it can allow us to see microfossils. So here we have a foraminifera, which is a little single-celled organism that floats around in the water. And as you can see, The foraminifera itself has this very, very distinct spiral shell, so different species of foraminifera will have shells which are completely different in appearance. And so what we can do is we can classify this particular foraminifera based on the shape of the shell, and that's very, very helpful to us because certain types of foraminifera, for instance, will only live in certain conditions. So you have cold water foraminifera, you have warm water foraminifera. You can have shallow water ones and deep water ones, etc., etc., etc. So by knowing the species and knowing where it occurs, it will also help you to try and work out what type of environment your sediment might have been deposited in. And then finally, we can really get into very, very high detail magnification. So this is a scanning electron microscope image, and you can see you have these plates that, you've got a stack of them here, and you can see an individual one right here. These are actually crystals of clay minerals. So most of the time, if you look down a microscope at a load of clay minerals, you won't be able to see anything. The crystals are just too small. However, when you look at them down a scanning electron microscope, you can resolve individual crystals, and you can, if you're lucky, be able to analyze those individual crystals, and you can work out exactly what clay mineral you're dealing with. And once again, this can be helpful in working out the possible environments of deposition, or working out what happened to the rock after it was lithified, just gauging what the history of the rock. So knowing the types of clay minerals you get can also be extremely important in working out the life story of the sample you're looking at. So where possible, the field data will be used to produce a geologic cross-section displaying the vertical and lateral facies relationships. So one of our goals is to understand the rock, but it's also to work out where the rock goes. Where does it start? Where does it stop? What's the morphology? What's its three-dimensional form? So using all this data, a comparison is made to a modern-day depositional system, and everything is combined to produce an environmental interpretation, which is where we work out the environment of deposition. So analysing the rock in this way not only makes for great science, but it also has uses from an economic point of view. So, for instance, by mapping and producing cross-sections, we can identify possible economic horizons. So an economic horizon is a layer of rock that has something that we can extract for money. Essentially, we can make a profit. So that would be something like oil and gas, or it could be something like uranium, for instance, or it could be gold, or all these types of material can occur in sedimentary rocks. We can also get mineralogical studies to help us identify those economic minerals. So just going back to the microscope, looking down the microscope, we can identify minerals in the rock, and if it just so happens that some of those minerals are useful to us, so let's say there's something like ilmenite or rutile in our sand, well, those are both titanium minerals, and if there's enough of them in your rock, you could in theory have a rock that you could process to extract the titanium, which would be pretty good. So by looking at a sandstone down a microscope, you can work out whether it's got the porosity and permeability to make it a suitable reservoir rock. That goes back to the oil and gas. We've already touched on that before. And then, of course, we have our microscopic and bulk analysis of things like mudstones, can tell us how much carbon is present, so we can gauge whether it would be, a good source rock for things like oil and gas. Because what you really want is you want a mudstone that's got lots and lots of carbon in it, because that will, if you heat up that mudstone, that carbon can change into hydrocarbons, which you can obviously then extract for profit. So, in terms of sedimentary rocks, they come in three varieties, and we've already touched on these in the past, but it's not going to hurt to discuss them again. So we've got detrital sedimentary rocks, also sometimes referred to as clastic sedimentary rocks. We have the carbonates, and we have the chemical sedimentary rocks. So the detrital, or clastic sedimentary rocks, are made of solid particles of a pre-existing rock or minerals that are compressed and cemented together to form a rock. So the classic example of that is something like a sandstone. The carbonates, well, they're formed from concentrations of shells, or should I say shelly material, or you can have the carbonate precipitated directly from water due to some kind of organic process, and this, these layers of carbonate material will build up over time, and that carbonate material can then be used to produce rocks, of which the classic example is limestone. And then finally we have the chemical sedimentary rocks. So those are produced by the deposition of dissolved phases, that means dissolved minerals, typically carbonates, but it can also be silica, so quartz. And the carbonate or the silica is dissolved in the water, and all you have to do is you have to encourage that mineral to exit the water. And so you have to do things like change the temperature, change the pressure, change the fluid chemistry, or maybe have some kind of organism in the system that will actually encourage that particular mineral to come out of solution. So just by changing the environmental conditions, you can encourage minerals which are dissolved in hydrothermal fluids to exit the hydrothermal fluid and precipitate out as solid minerals. So detrital rocks can consist of more than 100 possible minerals. However, when it really comes down to it, only 3 minerals are very common: quartz, feldspar, and clay minerals. Those are the those are the minerals that you'll come across a lot of the time in clastic sedimentary rocks. Now, the reason they're the most common is twofold. First of all, they are robust, so they're physically strong. So quartz and feldspar are tough minerals. And so that means as your sediment gets transported, the soft minerals get destroyed and they're gone, they're lost. However, the quartz and the feldspar will persist over time. So as the weak minerals get removed, that means your sediment becomes more and more rich in minerals like quartz and feldspar. The other reason why quartz, feldspar and clay minerals dominate is because the minerals can be chemically inactive. So this goes particularly for quartz and clay minerals. I should point out feldspar is also pretty chemically inactive, but quartz and clay minerals are really inactive. So once again, as your sediment gets transported, you not only have the physical processes acting on your sediment, but you also have chemical processes. So your minerals will be reacting with things like oxygen in the air, or they'll be reacting with the water in the river. And this will produce chemical reactions that over time will destroy minerals. And so if your mineral is chemically inert or pretty inactive, like quartz, it will just sit in the system and it won't get destroyed, whereas other minerals will slowly break down over time. So once again, that's going to encourage your sediment to become more and more rich in chemically inactive minerals. So over time, your sediments will become more physically mature and they'll become more chemically mature as well. And this leads to most sedimentary rocks containing, one or more of these 3 minerals. So you'll see lots of quartz, lots of feldspar, and lots of clay minerals in most detrital sedimentary rocks. So the composition of a detrital sedimentary rock is primarily controlled by the composition of the rocks in the area from which the sediment is derived, which is referred to as the source area. So, for instance, if your source area is very, very rich in granites, well, obviously the sediment you're going to produce by weathering that granite is going to have lots of quartz, lots of potassium feldspar, a little bit of sodium plagioclase feldspar, and maybe some biotite and some muscovite. You're not going to get things like olivine appearing in the sediment because the olivine just wouldn't be there. So the first control on your sediment is going to be the rock that's being weathered to actually make that sediment. However, as we've discussed, as that sediment gets transported, physical processes and chemical processes will change the composition. So the composition is affected by what's referred to as the degree of maturity. So this essentially says how long is a sediment being transported for. If it's been transported for a long time, it is a mature sediment. So that means as it's been transported for a longer time, you're going to have more time for these physical processes and chemical processes to take place. So chemically reactive and physically weak minerals will be stripped from the system, and the sediment you'll get at the end will be more rich in these chemically resistant and physically resistant phases. So as a geologist, when we walk up to a rock face and we see a rock that, for instance, is nearly 100% quartz, well, we can say, okay, this is a good chance that this is a mature sandstone, for instance, because clearly whatever process has been taking place has gotten rid of all the weak phases, and all we're left with now is just the quartz. At the other end of the scale, we can also have an immature sediment or an immature sedimentary rock. And this is when the sediment has not undergone significant transport. So this means our sediment is going to contain substantial quantity, or noticeable quantity, should I say, of these less resistant minerals. So we're going to see the types of minerals that normally would break down due to physical or chemical processes. Well, they'll be present in these sedimentary rocks. So just by looking at the minerals that we can see in our rock, it instantly gives us a bit of an idea about, how the sediment's been treated. And then straight away, once we know, once we can gauge whether the sediment is mature or immature, that's going to give us an idea about what types of environment the sediment could have been deposited into. So another thing we're going to look at is the clast size, so the grain size. How big are the clasts that make up our detrital rock? And obviously that's going to tell us something about the conditions of transport and deposition. So if you remember, when it comes down to clast sizes, essentially it goes clay, silt, sand, gravel, cobble, boulder. Obviously boulder's the largest, clay is the smallest. So if you have something that's a gravel-sized particle or a cobble-sized particle or a boulder-sized particle, well, obviously those types of particles are very large, they're very heavy, and so they can only be transported by the most energetic of processes. So you would need something like very fast-flowing water, you would need landslides, very, very strong waves in a beach environment, or glaciers to move these kinds of larger clasts. So if I see a sedimentary rock that contains a substantial quantities of gravel-sized clasts or cobble-sized clasts or boulders, well, I know that whatever environment that sediment was deposited in, it must have been a pretty high energy environment. And so once again, that limits the possible options. For instance, if I see a sediment that's got loads of gravel in it, well, I can instantly rule out something like a lake environment straight away, because that's a very low energy environment. Those sediments just wouldn't be there. So when we're dealing with sand-sized clasts, well, sand-sized clasts require an energetic to moderately energetic environment. So we're going to find sands associated with things like stream channels, so fluvial systems. We're going to find them in environments like wind-blown deserts, and we're going to find them in beach environments. We're also going to find them associated with these higher energy sediments as well, because remember, a high energy sediment high energy environment will not only transport large clasts, but will also transport medium-sized clasts and small clasts as well. So bear that in mind. At the bottom end of the scale, we have the silts and clays. These are obviously very, very small particles. It doesn't require much energy to move them, and so silt and clay-rich rocks are often associated with quite low energy environments. So things like slow-moving waters, like mature rivers, areas that have weak currents. So we might expect them to find them in environments like lakes, lagoons, the abyssal plain, the deep ocean, or the floodplains surrounding rivers. These very, very low energy systems where these very, very fine particles can settle out of the water because the water is almost stationary. Remember, if the water's moving just a little bit, it will stop the clay and silt particles from falling out of suspension. So what you really want is you want your water to be very, very still, and that will allow this fine sediment to leave the water and settle out onto the bottom of your lake, for instance. So if we look at our class sizes, so we've got silts and, that should say silts and clays. I apologise, I've written mud there, that should say clay. So we've got silts and clays at the bottom, the finest particles. We've got sands, the kind of medium-sized particles. Then obviously we have gravel, but then that also includes cobbles and boulders as well. So if I have a sediment that contains gravels, well, clearly that sediment can only have been transported in a high energy environment. Now, the thing about the high energy environment is because it's high energy, it can not only transport gravels, it can also transport moderate sized particles and fine particles as well. So a high energy sediment could have all of these different particle sizes in it. The thing is the way I know it has to be a high energy environment is because it has these gravel, cobble or boulder sized clasts, and that's what tells me this was a high energy environment. In terms of moderate energy sediments, obviously because it's a kind of intermediate energy level, well, it doesn't have the oomph to move large clasts, so your gravels, your cobbles, your boulders won't be present. But you will have medium-sized particles like sands, and you will have the fine particles like silts and muds. So for instance, river systems, meandering river systems, you would expect to get sediments within the river that are dominated mostly by sands, silts and clays, because that's a pretty, medium level environment. You wouldn't expect to get, coarse gravels, cobbles or boulders because the water just isn't moving fast enough. And then we obviously have low energy environments. Well, in a low energy environment, the transporting medium, something like the water, doesn't have much energy, so it can't transport large particles, it can't transport the medium-sized particles. The only types of particle it can move around are the very, very small particles, the silts and clays. And so as you can see, just by looking at the class size, I can make a very coarse estimate of the type of energy of the system. So in terms of the deposition of sediment, so that's the transportation energy. In terms of the deposition, what will I see? Well, in high energy environments, I'll tend to get sediments which are very, very rich in coarse sediment, coarse clasts. That's simply because as your fast moving medium, let's say your fast flowing river, starts to lose energy, obviously those big heavy clasts will get dropped quite quickly. So as soon as your energy level starts to drop, these big clasts get dumped straight away. So that means if you're moving them around, you can only really move them around and depositing them in these high energy systems. As soon as you leave the high energy system, the gravel and clay, the gravels, cobbles and boulders won't be in the sediment anymore. So you can only get them in these high energy depositional environments. Sands will tend to be most common in moderate energy environments, so environments like rivers and beaches, and silts and clays will be most common in low energy environments. So by looking at the class size, we can infer both the transporting energy and also in general what the depositional energy was. Was it a high energy environment, a moderate energy environment, or a low energy environment? We can also look at the textures. So we're going to be looking at things like the size of the clasts in our rock, the size distribution, which is referred to as the sorting. We're going to look at the shape of the class, which is referred to as rounding, and we're going to look at, is there any particular type of arrangement of the clasts? Now, in most sedimentary rocks, the clasts just get dumped, so there's no arrangement, but there are certain circumstances in which the clasts can be arranged, so there'll be a pattern to them, and this will help us to work out what the possible environment of deposition was. So the class shape is a reflection of the degree of rounding. How well or poorly rounded are your clasts? So the longer a detrital sediment, so that's a class bearing sediment, is transported for, the more opportunity it has for the clasts to hit each other. And so as those clasts are banging into each other over time, number one, they become more rounded. So every time a clast hits another clast, it will knock off a very, very small chunk of the clast. And so over time, sharp corners get knocked off and your clast steadily becomes more and more rounded. Obviously, because you're knocking off chunks from your clasts are also going to get smaller. So over time, what will happen, your larger clasts, so your boulders, your cobbles, your gravels, will all bang into each other and they will break themselves down. So, you'll take one cobble size clast and you will break that cobble sized class down to give you thousands of sand sized particles. And so this means that the longer the sediment is transported for, the more time that clasts have to become smaller, and so over time the size range of your clasts will steadily get tighter and tighter because the larger clasts are being broken down to make smaller clasts. And then finally we have what apparently is the size range, but it should actually say size range. Once again, I apologise for the mistake there. And this is our sorting. So as our class becomes smaller, the size range of class in our rock as a whole becomes tighter and tighter. So a very mature sediment, a sediment that's been transported for a while, will typically have well-rounded clasts. The clasts will typically be smaller, so you're not going to have larger clasts typically, so you're not going to have your boulders, your cobbles, your gravels. And we're also going to see quite a tight size range, so the sediment should on the whole be reasonably well sorted. Now there are other factors though. So for instance, something like the energy of the environment can also play an important part. So obviously in a high energy environment, your clasts are being moved around very, very quickly. And that means they'll hit each other a lot. And so this means your class will get rounded very, very fast because of all these impacts that are happening. So when we're looking at things like mountain river systems, so braided river systems, you'll tend to find those sediments contain lots and lots of gravel and cobble sized clasts because it's a very high energy environment. And those sediments haven't been transported too far from the sediment source, because remember, the sediment is coming from the mountain, so the mountain rocks are being eroded to make the sediment. That sediment is entering these braided river systems in the mountains, and it's being transported. So the sediment hasn't actually been transported very far, it's still in the mountains. But because the transporting medium, the river, has lots of energy, it's causing these cobble and gravel-sized clasts to constantly bang into each other and to slowly round themselves off, or should I say actually quite quickly round themselves off. And so this means that these high energy river sediments will contain quite coarse clasts, but those coarse clasts will often be quite well rounded because of the energy, meaning there are so many impacts. In contrast, silt and, that should say clay, I don't know what was going through my head. So in contrast, silt and clay sized particles are transported in suspension, so they're actually held in the water or they're held in the air. And so they very, very rarely collide, and as they don't really collide, that means they won't round. So when we're talking about the roundness of a particle, we're only really talking about boulders, cobbles, gravels and sands. Anything smaller than that doesn't really round because the particle is just too fine. So in terms of our class size distribution, when we look at a sedimentary rock, we typically refer to it in a couple of ways. It can either be well sorted, which means there's a tight range of class sizes, so there are, the size range isn't that big. Or you can have a poorly sorted sediment, in which case you have quite a broad range of class sizes. As we've discussed, typically the better sorted your sediment, the longer it's being transported for. So a well sorted sediment is very often a mature sediment. So the reason for this is, of course, as we already touched on, as a sediment gets transported, bigger clasts get broken down to form lots and lots of smaller clasts. So you'll lose larger clasts over time, and that means your size range of class sizes in your sediment will steadily get tighter the longer it's transported. Now, once again, the strength of the transporting medium is going to play a part in this. The more energetic the system, obviously the faster those clasts will bang into each other, the faster they'll wear each other down. And so, they'll very quickly get smaller the more high energy the environment. So once again, we have to factor that into our analysis as well. So in terms of sorting, here we have one of the classic diagrams. So you can see these are our range of sediments here. So up here we have a very well sorted sediment. You can see the clasts are almost completely the same size. And down here we have quite a poorly sorted sediment. We can see the clasts are a range of different sizes. So we have a very tight size range here. So this is well sorted. And we have quite a broad size range for clasts down here. So that's poorly sorted. And so if we look at these two examples, we can see, the different situations. So here we have our sandstone again that we saw earlier. One of the things you'll notice is these quartz crystals are actually pretty much all the same size. And so this is going to suggest that what we're looking at is a very well sorted or well sorted sediment. And so this is going to help us identify the possible environment in which this sandstone formed. Because once we know it's well sorted or very well sorted, then we can say, right, what environments would I expect to have a very sand-rich, very well sorted or well sorted sediment forming in? And once I know those environments, I can get rid of the environments that it probably wouldn't have formed in, and I can focus on those environments which are the most likely. Now, if we look down here, on the other hand, here we have ourselves a nice conglomerate. You can see quite clearly we have these cobble-sized clasts here. Note how they're quite nicely rounded, though. So they are quite well rounded, but the rock itself is actually pretty badly sorted. So you can see you've got cobble-sized clasts like this one here. You can see you've got some gravel-sized clasts, these smaller ones down here, and you can see how the matrix of this particular conglomerate looks kind of gritty. And that's because the matrix is dominated by sand. And so what you're looking at here is quite a poorly sorted rock. You have cobble-sized clasts, you have gravel-sized clasts, you have sand-sized clasts. So you have quite a broad size range. And so once again, as a geologist, what I'll do is I'll think to myself, right, what type of sedimentary environments would I expect to find a poorly sorted sediment like this forming in? And then once I'd come up with the possible options, I would then go, right, which one of those sedimentary environments would I expect to find rounded clasts in as well? So I not only have a poorly sorted sediment, but I also have one that has quite rounded clasts. And so that's going to help me once again refine the possible environments of deposition. And so this is one of the things that a geologist is aiming for when looking at a sedimentary rock. Okay, so this is a great place to stop. So pause the video, get up, have a walk around, take a few minutes, and then please come back for part 2.